Okay, so we can be more specific. We can say that quantitative data is either continuous or discrete, and we can say that qualitative data is what or what? Nominal or ordinal. Okay, so coastal wind speed. Okay, coastal wind speed. Would that be quantitative or qualitative? It would be quantitative. Okay, it would be numerical. Would it be continuous or discrete? That's right, it's measured on a continuous scale. Okay, if you see a coastal wind speed written down, it must have been rounded, because theoretically you could measure to any number of decimal places. Okay, what about the number of crew on a ship? Would that be continuous or discrete? That would be discrete because it's based on counts. Now, nominal, ordinal. The origin of a ship. Okay, UK, Europe, North America, Africa. Okay, these are categories with no logical order, so therefore it's nominal. What about ship size? Small, medium, large. What would that be? That would be ordinal. But why are we doing any of these things? What is the advantage of classifying your data as a certain type? Because there are various tools and techniques that we can apply when we have quantitative data, and there are other tools and techniques that we can apply when we have qualitative data. So therefore, it makes logical sense at the start of your analysis to classify your data as a certain type. Now, after data types, what did we do? We did descriptive statistics. Okay? So, rather than looking at a whole data set, sometimes it's useful to summarize your data set. Okay, sometimes it's useful to summarize your data set just with a single number. Now, your single number might be a measure of location. Okay, so what do we mean by a measure of location? Okay, there's a short word beginning with S. Size. We'll come to spread shortly. Okay, the short word beginning with S that we can think of when we hear measures of location would be size. Now, I gave you this data set last week, 3, 4, 5, 5 and 8. Now, I was asked a question in the computer practical last week. Okay, because here, if you look at this section in a rectangle, what does it say? Suppose we have a random sample of size n. Okay? Now, I don't want you to get confused between sample size and when I say a measure of location tells us about the size of the values. Okay? They're two different things. Look at this data set here, 3, 4, 5, 5 and 8. How many numbers do you see? 5. How many observations do we have? 5. Okay, so the sample size is 5. But a measure of location tells us, well, how big are these values? Okay, how can we summarize the size of the values just with one number? okay, we would need a measure of location. Okay, so last week we covered 3 averages that all begin with the letter M. What are they? Okay, we covered the mean, we covered the median, and we covered the mode. Okay, so you've got the equation there for the mean. Okay, so what symbol do we use for a mean? Okay, X with the line above it, which we read as X bar. Now, I asked you the question last week, what is the best average after we'd covered all 3? And what did we agree on? There is no best average, okay? It depends on the situation. When is the mean particularly useful? What does the mean use that the other averages don't use? All the data, well done. Okay, the mean is the only average that uses all of the data. What about the median? Okay, what is a median? Okay, so the mean is all the values added together divided by the sample size. Okay, so the mean of that data set was 25 divided by 5, giving us 5. What about the median? What is a median? Someone said it. It's the middle value. The middle value. But if you're doing it by hand, what do you have to do with your data set to start off with? Arrange the data in ascending order. Okay? Now, the median has an alternative name that was mentioned by someone here. The alternative name for the median would be the 50th percentile. Okay? Because we also have the lower quartile, which has the alternative name. The lower quartile is also called the 25th percentile, and the upper quartile is also called the 75th percentile. Okay, but the quartiles, they're not averages. Okay, third average, also beginning with M, was the mode. Okay, what is the mode of a data set? What does the French word mode mean? Fashion. The mode is the most fashionable value, the most popular, the most commonly occurring. Okay, so the mode of this data set was also 5. Okay, so modes tend to be very useful when you've got actually categorical data, okay, when you've got qualitative data. Okay, so the example we used last week was, imagine as a group we were stood on Claremont Road and we were looking at the frequency of colours of cars. Okay, if red was the most frequent colour, we could say that red is the mode. Okay, so you don't actually have to be working with quantitative data to work out a mode. Now, if you just take a moment to read this section here. Okay, just this section here. Okay, so this should tie in with what we mentioned last week. Okay, if your data set is fairly symmetrical, which measure of location you use, it's not really going to matter too much. However, if your data set is not symmetrical, okay, if there are outliers, very unusual observations in your data, they will have a big impact on which one? Outliers will have a big impact on the mean, because the mean uses all of the data. Okay, so after measures of location, okay, and when we hear location we think size, we covered measures of dispersion, okay, measures of dispersion or measures of spread, okay. So location is size, dispersion is spread. The most basic measure of dispersion would be the range, okay. To work out a range you only need two values, okay. It's maximum minus minimum. So what will greatly affect the range? What will greatly affect the range? The extremes, okay. The calculation only uses the extremes. So if your data set contains outliers, that will have a massive impact on the answer. So what statistic could you use? What statistic could you use to quantify spread that would be more stable than the range? Something that we discussed last week. Instead of the range, you could work out the IQR. What's the IQR? The IQR is the interquartile range. Okay? Now that name, the interquartile range, describes what it is. Okay? It is the range between the quartiles. 25% of the data is less than or equal to the lower quartile, and 25% of the data is greater than or equal to the upper quartile. So therefore, the interquartile range would be the range of the middle 50%. Okay, so the equation for the range, what is it? The equation for the range would be max minus min. And what's the equation for the IQR? Upper quartile minus lower quartile. So you're not actually using much information. So what if you want to measure dispersion? Okay, what if you want to measure spread, but you want to use all of the data? What do you do? What did you do in the computer practical? What did you do in the computer practical last week? What did you work out? The standard deviation or the variance. So, are you all happy with the way that we describe in words this equation? Okay, this equation, the most basic equation, the one for the mean. Okay, we've got a Greek letter, haven't we? What's that Greek letter? The Greek letter is sigma, and what does it represent? Sum. Okay, so to work out a mean, you sum the observations, okay, you sum the values, and you divide by, what do you divide by? The sample size, yeah? Lowercase n. So, using that logic, I want you to now describe that equation. Okay, so just that equation there. Okay, does anyone have a description? A description of this equation in words that they would like to share with the group? Okay, so to understand that equation, because it's more complicated, we will just apply it to a basic data set. Okay, so in your notes, I want you to write down 3, 7, and 5. Okay, so imagine you've been asked the question, work out the variance and the standard deviation of 3, 7 and 5. Okay, so that's the equation there. Now remember that on this module we're not going to focus too much on the theory. We're interested more in application. However, you know, to understand this one, okay, to understand what a variance is and what a standard deviation is, we need to see the equation in action. So, can anyone answer this question? Before you work out a variance, okay, so the symbol that we use for the variance is s squared. Now if someone asks you the question, before you work out a variance, what do you need to work out? What would you say? Can you all see that before you work out the variance, you have to work out the mean? So, 3, 7 and 5. What's the mean? Okay, so the mean is 5. Now, how is the mean being used in that equation? X bar is the symbol for the mean, and how is it being used? We're subtracting it from x. And what does x represent in these equations? What did x represent in the equation for the mean? It's just the values, isn't it? Okay, so each value, okay, each observation will have the mean subtracted from it. Okay, that will give us a series of deviations, and what's happening to those deviations? They're being squared, and then those squared deviations are being summed. Okay, so applying it to our data, would you all agree? Okay, would you all agree that that is the top of the equation? Okay, that's the top of the equation. And what's on the bottom? Okay, 3 minus 1, sample size minus 1. Okay, so let's work out the answer. What is it? 3 minus 5 gives us minus 2 squared gives us 4. 7 minus 5 gives us 2 squared, 4. Okay, 8 divided by 2, the answer's 4. And how do you get the standard deviation from the variance? What do you have to do? You take, okay, can you all see that in the notes? Can you all see that in the notes? To get the standard deviation from the variance, you just take the square root. Okay, so what multiplied by itself gives us 4? The positive root we know is 2. Okay, so is everyone happy with that being the answer? Variance 4, standard deviation 2, yeah? Right, so what I'd like you to think of before we move on, okay, what I'd like you to think of before we move on is, what would the answer have been if our data set was 5, 5 and 5? 0, okay? So 5, 5 and 5, the mean is still 5. And the answer here would have been 0. And would you all agree that that makes sense? Because what we're trying to quantify is spread, dispersion. And this data set has got no spread, no dispersion. Now 3, 7 and 5 does have spread. So, can anyone answer this question? When we work out the deviations, why are we squaring them before summing them?
There are chances that the value comes negative. So
That's correct, yeah. Can you all see that we would get cancellation if we didn't do that? Okay? Think of the equation being used if we didn't square the deviations. 3 minus 5 equals minus 2. 7 minus 5 plus 2. So the minus 2, the plus 2 would cancel each other out. So we would have 0 on the top of the fraction. And if you've got 0 on the top of the fraction, it doesn't matter what's on the bottom, the answer would be 0. So, in answer to the question, why do we square the deviations before summing them? It's simply to avoid cancellation. Now, final question, what is the advantage of taking the square root of the variance to give us the standard deviation? What's the advantage of taking the square root of the variance? Well, what's the opposite of squaring something? The opposite of squaring would be taking the square root. Now remember that up here we squared the deviations. Why did we do that? To avoid cancellation. But you must do the opposite of that. You must do the opposite of that. Why? Well, think about the units of measurement. Okay, think about the units of measurement. Imagine you're looking at coastal wind speeds. Okay, imagine you're looking at coastal wind speeds in miles per hour. Okay, so if the units is miles per hour and you've worked out the variance and the standard deviation, which one of them will also be measured in miles per hour? It would be the standard deviation. Okay, so the variance is not measured in the same units as the raw data. Okay, why not? Because you squared the deviations before summing them. You have to do the opposite of that to return to a statistic that is. It also actually has an easy to understand interpretation, the standard deviation. What was the standard deviation of our data set? 2. Okay, what was it? 3, 7 and 5. So what's the mean of 3, 7 and 5? We know it's 5. How far is 3 away from 5? 2. How far is 7 away from 5? 2. What's the average of 2 and 2? 2. Okay, the standard deviation tells us how far, on average, each value is away from the average. And again, just like you had a choice, okay, just like you had a choice over whether to use the mean or the median when you've got quantitative data, you've also got a choice now with your measures of dispersion. So what I'd like you to do is just take a moment to read that section. Okay, so if your data set is fairly symmetrical, you tend to use the mean as your measure of location and the standard deviation as your measure of dispersion. Okay? The mathematical properties of the mean and the standard deviation are very simple. But if your data is not symmetrical, okay, you might use the median as your measure of location and perhaps the interquartile range as your measure of spread. Okay, so after descriptive stats, what did you do last week in the computer practical? You produced graphical displays, didn't you? Okay, so which graphical displays did we cover in the practical last week? We did one beginning with H. We did a histogram. What else? We did box plots. We did another one beginning with B. Or at least we saw another one beginning with B. Does anyone remember the bar chart? Okay, so how do you pick a graphical display? What was the first topic that we covered last week? What's the first thing that we recap today? Data types, yeah? Okay. So, in column 1 here of Minitab, can you read this at the back okay? Column 1, we've got some wind speeds. L1 just means location 1. Okay, so at a certain location we've recorded wind speed. Okay, and how many values do we have in column 1? I think it's quite a lot. Okay, it's 1,000 values. In column 2, we've got some more wind speeds at a different location. Now, what data type is this? This data type in columns 1 and 2 would be continuous. Okay, it's quantitative continuous. So what graphical display would you think about producing for this data type? Okay, what graphical display might you think about producing? Well, these are histograms. Okay? Now, this is a bit small, so I might need to read this out for those of you at the back, but I've just hovered over one of the bars, and it says value equals 69, bin equals 19.9 to 20.1. What does that mean? Well, what data type did we say this was? Wind speed. Continuous? So what does it really mean for a variable to be continuous? If we've got 1,000 wind speeds, what can we say about them? If we measure to enough decimal places, would you agree that all of the wind speeds will be different?
Yes.
Yeah, because theoretically we can measure to an infinite amount. So, what does this mean? We know that the 1,000 wind speeds will all be different. This says value equals 69, bin 19.9 to 20.1. What does that mean? It means that 69 of the wind speeds will be between 19.9 and 20.1 miles per hour. Does that make sense? Now, histograms are quite useful for allowing us to understand location and dispersion. But what are they not very good for? What if you're asked this question? You've got two locations here. At which location are the wind speeds larger? At which location are the wind speeds more spread out? Can you see it's quite difficult to make that comparison when you've got two different histograms? So what might you do instead? okay, you might produce box plots instead. Would you all agree that this difference now between location 1 and 2, it's more obvious? Okay, so that's histograms and box plots. What about if this was your data? What would you think about producing? The origin of a ship and the frequency. What could we produce? Okay, what could we produce? What's this? This is called a bar chart. Now, which one does it remind you of that we've already looked at? It reminds us of, perhaps, histograms. Okay, what's the similarity between histograms and bar charts? On both of them you see vertical bars. The y-axis of both of them is frequency. But what's the difference? Well, visually, would you all agree that a visual difference would be, with a histogram, no gaps between the bars, and with a bar chart there is. But why is that? It's because of the data type. Okay, with histograms the data type was continuous, and with bar charts the data type is that quantitative or qualitative? Well done, it's qualitative. Okay, so that's our graphical displays. Now in the computer practical today we will also be thinking about probability. Okay, so I would just like you to read that first paragraph. Okay, this is page 11 of your notes. Okay, so last week there were several definitions of the word statistics, and there were several definitions of the word population. Again, with probability there'll be many different definitions, but I think this is quite a good one. Probability, okay, a simple definition would be it's long run relative frequency. Okay, because let's say that we've got some activity, okay, some experiment, some trial that's very simple, like tossing a coin. Okay, so tossing a fair coin. We know, don't we, that the probability of heads is a half, the probability of tails is also a half. Now, what if we look at the number of times heads occurs and we divide that by the number of trials, the number of times the coin is tossed? Would you all agree that if the coin is only tossed once, okay, if the coin is only tossed once, okay, so here n is the number of trials, the number of times the coin is tossed, and what's R? The number of times heads occurs. Okay, so I want you to imagine the coin is only tossed once. Okay, if the coin is only tossed once and the result is tails, what would be the probability of heads using that equation? It would be 0, wouldn't it? And if the answer is heads, okay, that equation would give us an answer of 1. But we know intuitively the answer is 0.5. Okay, so this only works as n tends towards infinity. Okay, so if you toss the coin 1,000 times, okay, you'd have to be pretty bored to do that. But if you did toss the coin 1,000 times, when you divide the number of heads by 1,000, you would expect the answer to be close to 0.5. Okay, so something that crops up in probability theory would be the multiplication rule. Okay, so if you just read it here, the multiplication rule. Now, I'll say now that what we're going to do this week, it's quite theoretical, okay? It'll be a lot more useful next week. So, those of you that have done stats in the past, okay? Those of you that have read research in marine science or written research, has anyone come across t-tests? Can I just get a show of hands who's come across t-tests? No? What about ANOVA or regression or correlation? Any of these words ring a bell? Okay. Don't worry if they don't ring a bell, because that's what we're going to do in the rest of the course. Okay? But all of these different techniques, okay, t-tests, ANOVA, regression, correlation, they all result in p-values. Okay, and what's a p-value? Any guesses? P stands for probability. Okay, so this week it's just a bit of theory on probability. So, what is the multiplication rule? The multiplication rule would be, if you're trying to work out the probability of two events, A and B, then it equals the probability of A multiplied by the probability of B. However, that only works if the events are independent. Okay, so imagine this was your problem. Okay, it's sort of a marine example. Okay, a ship is chosen at random. And you've got these two events, okay? Event A is crew greater than 10. And event B, tonnage, is greater than 1,000. And you're asked this question: work out the probability of A and B for a randomly chosen ship. So my question is, could you use the multiplication rule? Are these events independent? What do you think? So using your common sense, if a ship has a very large weight, could that have an influence on the number of crew? It's possible, isn't it? It could do. So therefore, if the events are not independent, it means that you cannot use that rule. Okay, now as well as the multiplication rule, you might have guessed, there is an addition rule. So if you turn to page 12 of your notes, okay, turn to page 12 of your notes and just read the addition rule. Okay, so generally speaking with these probability questions, if you see the word and, that makes you think of the multiplication rule, okay? But if you see the word or, that might make you think of the addition rule. So, if you're interested in the probability of A or B occurring, you would use this addition rule. We will see it applied now to another marine example. Okay, so just read through that scenario. Okay, so R would be defective radar, and E is defective echo. Now, can you all see that the probability of R and E occurring, okay, this here, we were told it was 1 in 100 ships would suffer from defective radar and defective echo. Now, can you all see that 0.01, well, that clearly isn't 0.05 multiplied by 0.03, because we haven't used the multiplication rule, because these events are not independent, okay? We were given that information, okay, in the scenario. So using all that information, we could work out that the probability of a randomly chosen ship having a defective echo or a defective radar would be 7%. Okay, so that's just basic probability theory. Now, once you move past that basic probability theory, what do we think about? Well, we think about distributions. Now, again, just a very quick recap. Location means size, dispersion means spread, and distribution means, there's another short word beginning with S. Location is size, dispersion is spread, distribution is shape. Okay? Distribution is the shape of the data. Now, you've got discrete distributions when you're dealing with counts, and you've also got continuous distributions. Okay, so in your notes you've got some information on the binomial distribution and the Poisson distribution. Okay, they're both discrete. Okay, so two discrete distributions, and then after that you've got the normal and exponential distributions. They're for continuous data. So you might want to just have a quick look at that information in the square, just those bullet points. Okay, so how do you spot whether a question might require the binomial distribution? Well, there will always be a fixed number of trials, there has to be, and each trial can only have two outcomes. Okay, and the two outcomes using standard wording would be success or failure. Okay, so tossing a coin as an activity has two outcomes. We could use the binomial distribution. Okay, why would we do that? Well, if I say to you the coin is tossed once, the probability of heads we know is 0.5, but if I say to you the coin is tossed 12 times, what's the probability of 6 heads, 6 tails? It becomes more difficult. Okay, so that's when you would use this equation. It's not an equation that you need to remember at all. Okay, so you don't need to remember the equation. To answer a question like this, you will simply use Minitab. Okay, so in the computer practical, you'll have to do this. Okay, just read through the example. Okay, so we've got 12 beaches. That's a fixed number of trials. The probability that any beach would pass one of these EU hygiene regulations is 0.95. Okay, so we have the correct type of scenario to apply the binomial distribution. Okay, because the beach will either pass or fail the regulations. Okay, so there's only two outcomes. So using this program that you used in the practical last week, okay, you would simply go to Calc, probability distributions, binomial, and what's the number of trials? How many beaches were there in total? There was 12. And the probability of a beach passing the regulations was 0.95. And as an input constant, you would enter 9. Well, the reason that you don't enter 10, because this is less than or equal to, okay? You ask the question less than 10. That means less than or equal to 9, okay? So the answer would be 0.195683. So about 2%. Okay, we're not going to go right through the Poisson distribution because you know, you'll get a chance to apply it in the computer practical. All I'll say for now is it's another distribution for discrete data, okay? But now there are no fixed number of trials, okay? So whereas with the binomial distribution there was a fixed number of trials, with the Poisson there isn't, okay? And also the parameter for the Poisson distribution, a Greek letter here. That Greek letter is lambda. Again, as opposed to knowing what the Greek letter is, it's more important to know what it represents. And here it represents a rate. Okay, so it's not a probability on a scale of 0 to 1, it's a rate. Okay, so you'll get a chance to apply that in the computer practical. But really, the most important distributions, certainly as far as what we're going to do on this module, will be continuous distributions. Okay, now the most famous distribution of all, okay, the most famous distribution of all would be the normal distribution. Okay, the normal distribution has got two basic properties. Does anyone know what those basic properties are? Well, if someone asked you to describe this shape, what would you say? Symmetrical and bell-shaped. Okay, those are the two basic properties of the normal distribution. It's symmetrical and it's bell-shaped. Does this shape remind you of anything that I've produced in Minitab already? What graphical display looked symmetrical and bell-shaped? It was the histograms, yeah? So when you've got real data, okay, because this is a theoretical distribution, when you've got real data and you want to know whether it's normally distributed, what would you do? You would just produce a histogram. And if your histogram is symmetrical and bell-shaped, well, that's the normal distribution. I'll just solve one problem related to the normal distribution, because this is again something that you will do in the practical. There is a horrible equation underlying it that you don't need to remember. But what I'd like you to read is just that example. Can you all see a Greek letter there? Can you all see that Greek letter? What is that Greek letter? Mu. I've been told by Greek students it's pronounced mi. Well, whether it's mi or mu, if you see that symbol, what is it? It's the mean average. Now, what symbol were we using previously for a mean average? X bar. Okay? X bar is the symbol that we use for a sample mean. Mu, or mi, is the symbol that we use for the population mean. Okay? What symbol did we use? What symbol did we use for a standard deviation earlier? S. That's a sample standard deviation. What's this letter here? That little letter there. Okay, that Greek letter is sigma. Okay, we've already mentioned sigma today. Summation, that was capital sigma. That's lowercase sigma. But again, knowing what it represents is the important thing. What does it represent? S was the sample standard deviation. Sigma is the population standard deviation. Okay? So, using that information, the mean 2.23, standard deviation 0.63, assuming the lengths are normally distributed, find a proportion of welds less than 1.5. Okay? All you would need to do is go to the normal distribution. What was the mean? Was it 2.23? Okay, what was the standard deviation? And what are we being asked? What proportion are less than 1.5? Is that right? Click OK. OK, and you've got the answer. And that's all you'll have to do in the practical. OK, so that's the end of this lecture. And now we've got the session up in the computer cluster on the 3rd floor.
Seminar and I
Right.
don't have the book where I can find.
Well, I can give you some. I've got some in my office. So after the
Yeah, we can. Yeah, okay.
Fine. How are you?
You don't have the course notes. I've got some in my office. I'll give you them after the practical.
After the practical. Sorry. Because I missed the first lecture.
You need the notes?
Yes.
All right. I've got some in my office, so we'll go back to my office after the practical if you've got the time.
All right.
And I can give you them.
Okay.
Then.